In this lesson, we're differentiating the inverse trig functions. So there's a couple of things we need to be able to do in this course. We need to actually be able to differentiate the functions, but that's quite straightforward because all the formulas that you need are on your reference sheet, and you'll have those in any test or exam that you do, and they're quite straightforward to apply. But we also need to know how to prove the results. Now, when we're deriving them ourselves, it's quite straightforward. We really need to just rewrite each equation using sine, cos, or tan instead of inverse sine, cos, or tan. And then we differentiate those equations using the known trig derivatives. And we can use dx, dy to create dy dx by taking a reciprocal and a couple of tricks along the way. Now, one thing we do need to do is keep track of the restrictions in the domain to explain why we chose positive and not negative square roots for the sine and the cos example. You'll see that in a moment. So let's start with the first one. If we look at y equals the inverse sine of x, then we can rewrite that as the sine of y equals x. So let's write it as x equals sine y. Now we know that that is the exact same curve, it's just written differently. And let's think about what that curve actually looks like, just for a bit of revision here. So we're on the same page. We know that it goes between 1 and -1 on the x-axis, and on the y-axis it goes up to pi on 2 and down to minus pi on 2. So when we write this, we can write the restriction in here, which is that y sits between negative pi on 2 and pi on 2, and that's an important consideration. So it's basically the fourth quadrant, or I think of it as the -1th quadrant, even though that sounds silly, and the first quadrant that y is sitting in. Okay, so next we can say, all right, what is dx dy? We can differentiate x with respect to y and say it would just be cos y. Now, it's tempting here to say, all right, dy dx then must just be the reciprocal of that. It'll be 1 over, and it's tempting to write cos y, but we don't want to do that. Have a think about why not. If we've started with y and we want dy dx, we want to differentiate y with respect to x. Now, paying respect to x means having x as in our answer. We wouldn't be paying proper respect to x if we didn't have x in our result. So we can't finish it with 1 over cos y. We need to come up with some sort of expression for cos y that has x's in it. So that's quite straightforward to do. Over on the side here, we can say, look, we know this identity well now. Cos squared y plus sine squared y, or the other way around, is equal to 1. So if that's the case, cos squared y must be 1 minus sine squared y. And then to find cos y, we can take the square root of both sides. Now, when we take a square root in this situation, don't we normally say, but it could be the positive or the negative square root? We would. But in this case, we don't need that. And the reason that we don't need that, and the reason that we can just take the positive square root, is because, and we should take note of this if we're deriving the formula, we should say, but cos y is positive in the first and the fourth quadrants. Now, those are the two quadrants that our graph is existing in. So if cos of y is positive there, then really cos y couldn't have been negative something or other. It has to have been positive. And that allows us to be sure that this is a good expression for cos y and that we don't need to consider both options. So at this point, we've got cos y is equal to all of this, and we could think about putting that in. Now, I want you to tell me, what do you think would be the problem? Can I write 1 minus sine squared y? Is that any better than what we had? No, it's still got y's in it. Okay, well, why did I bother doing this then? Can you see what sine squared y could be written as? Have a look over here. Sine of y is x. So sine of y all squared would be x squared. And we can put that in as an extra line here. Cos of y is equal to 1 minus x squared. And I suppose if you're being really thorough, you could say, since x equals sine y, which of course is written over there. So now we can take this result and we can bring it across, and we have 1 minus x squared. And we have now a formula for dy dx when y was equal to the inverse sine of x. Now, deriving the result when we're using inverse cos of x is going to be quite similar. So let's keep some of this here, and we can just change things around a little bit. If we have inverse cos x, then we can rewrite that as cos of y is equal to x. Okay, now this restriction isn't right because remember, if we're thinking about our inverse cos curve, it looks like this, and it goes from 0 up to pi, still 1 to minus 1. And so we would have to say that y is between 0 and pi. So in other words, y is in the first or the second quadrant. Okay, when we take dx dy then, we get minus sine y as our result. And now over here, instead of generating an expression for cos y, we want an expression for sine y. So really we can change this to sine squared y is equal to 1 minus cos squared y. And that means that sine y is equal to 1 minus cos squared y. Now we need to be careful to consider what what sine y actually is here. Now, if we are in the first and the second quadrants for y, then if we take the sine of y, well, the first quadrant and the second quadrant, sine of y will be positive, won't it? So again, we don't need to consider the negative square root, only the positive one, but we would write that the reason is that sine y is positive in the first and the second quadrant, and that's where we are. And so then we could say, all right, sine y is going to be 1 minus, and we've got the exact same situation here, where x is cos y, so x squared is cos squared y. So we've got the same reasoning happening. So these two results are very similar to work with. Now, the one difference that we have is we've got a negative there. So then when we take the reciprocal of this, so that finding dy dx is 1 over dx dy, or the reciprocal of dx dy, we want 1 over negative sine y. Now, that negative could sit down the bottom, but it's much neater to write it up the top. And again, sine y is 1 minus x squared, all inside a square root bracket. So the result looks just like the one before, except for it has this important negative sign out the front. Now, deriving the formula for the derivative of inverse tan x is similar, but just slightly different from the other two. Again, we'll start by saying the tan of y is x. So in other words, x equals the tan of y. And then we know how to differentiate x with respect to y here. We would say it's sec squared y. And remember, that means sec y, all squared. Now, to get an expression here in terms of x, we can again do some work on the side and say, look, we know this. And if we use this to derive the one that has sec squared in it, well, we're going to get that by dividing all three terms by cos squared. And that gives us tan squared y plus 1 is equal to sec squared y, which should also be familiar to you. So at that point, we can say, well, if sec squared y is equal to tan squared y plus 1, we can just sub all of that in straight away over here. And we don't have to consider quadrants or positive square roots or anything like that. So this one is actually a little bit more straightforward. But again, we don't want y in our result. We want it in terms of x. And changing it is quite straightforward. Since x equals tan y, then x squared will equal tan y squared. And you can write that down if you like. Tan squared y is equal to x squared, since tan y is equal to x. So therefore, sec squared y is really this, which is x squared, plus 1. And that gives us our simple result here for dx dy is x squared plus 1. Now we need to take the reciprocal of that, because we don't want dx dy, we want dy dx. So we literally get 1 over x squared plus 1. Let's have a look at how to use these now. Now these are the basic forms which we just generated ourselves, so we know now how to do that. These are the more complex forms, and in fact these are the ones that are on your reference sheet. So if you are differentiating the inverse sine of some function of x rather than just x itself, it makes sense that you will be putting f dash x into your formula. And we'll see how to actually derive these using the formal version of the chain rule in one of our examples, so that you're actually able to do that formally if you need to in an exam. Now in our first example, we need to differentiate y equals x inverse tan of x. Now straight away here I can see that I'm going to need the product rule, because I've got two separate functions of x, the x part and the inverse tan x part. So if you like to do it this way, writing your ingredients on the side, that's great. If you hop straight into it and find that you never make mistakes that way, that's also okay. So if u is x, u dash is 1, and if v is inverse tan of x, then v dash is 1 over 1 plus x squared. So now I could say that dy dx, or you could say y dash, is equal to v u dash, so I've got the inverse tan of x, plus x times all of this. Now if I'm multiplying this by this, I can literally write it with the x on the top of the fraction, and I can stop there. There's no real need to tidy that up or change it to a different form. It's done. In this second example, we are going to use the formal version of the chain rule to prove these results here. So the formal version of the chain rule just says, take any nasty looking section, in this case the ax plus b, and just call it u. When you've done that, you've effectively got y equals the inverse sine of u. Now there's two things you can do with that. You can say I can differentiate u with respect to x, and that would just give me a, but I can also differentiate y with respect to u, and here, if I'm just using one of these formulas, I get the exact same thing when I'm differentiating inverse sine of u as I would if I'm differentiating inverse sine of x. What I get is 1 over the square root of 1 minus u squared, and instead of an x there, I've got a u, so I put a u down here. Now we say dy dx equals dy du times du dx. And that means we need to do a multiplied by all of this. So then when we write it out, we can put our a in, but we're always careful not to put u into our solution, because in the beginning there were no u's. We just used that as a little workaround. So instead of writing u squared here, we'll write what u equals, which is ax plus b, and we'll square that. So we end up with this result. Now you can see that if we just had some function of x here, let's call this f of x, and we hadn't known the formula for it, then we could have followed through and done the exact same thing, except when we had differentiated u, well over here we would just get f dash x, because differentiating f of x you get f dash x. And here we would have got the exact same thing, and so in the end we would have actually had f dash x here over 1 minus, and then here we would have had f of x squared, and that would sit inside our square root bracket, and that's the result that we can see up here. In this third example, we have the inverse tan of some function of x, so we can go ahead and just apply this formula here. Now it might be handy, if you like to just point out what your function of x actually is over on the side, and then say therefore f dash x is going to be the derivative of that, which in this case is 5 e to the 5x. That way you've got the bits you need to just throw straight into your formula. So you can say here that dy dx is equal to, we need f dash x on the top, and on the bottom we need 1 plus our function of x squared. Now a little bit of working that you can do to tidy these sort of things up, you might in the beginning start writing things like this, and then realise, hold on, it would be nicer to simplify that and say I'm raising a power to another power so I can multiply the powers together. So really it would be neater to call this e to the power of 10x. Now you can see what you need to do there as you're writing it down, and then just pause, work it out, and put the 10x straight down, or you could do another line of working, I suppose, and tidy it up on the second line, up to you. Writing this on the side, again, is very optional. I recommend doing this in the beginning until you get the hang of using these formulas, and then after a while you might find that you don't need to write those and you can hop straight in.